Okay, well, if nothing else to go over, then I figured we would get into the next lesson on repetition today. And at the risk of sounding like a broken record, the concepts here for looping, just like they were for selection last time, are probably somewhat familiar, if not very repetitive to hear these things. I'm going to try to not belabor the fact that what looping is, because you've had COP 1000, you should remember how to do this, at least in Python. And so we'll focus specifically on what patterns are available or what keywords are available to us to implement the patterns that we're familiar with already, but as they specifically relate to Java. So in this chapter, we get into the while keyword, for keyword, do ... while, and nested. We'll talk about all those kind of variations, see some examples of it, and go from there. The book talks about loop performance a little bit, and it's an interesting topic. I'm not going to get into it very much in depth as it relates to looping, simply because the kind of things that they're talking about in the chapter with respect to performance are sort of applicable in general to programming, not just loops. So I don't see any need to go over them in the context of loops, but you should definitely read those things. Like, for example, comparing to zero is the most performant way to do comparisons when you have the option. If you've got a variable that could be zero or something else, check to see if it's equal to zero, not the something else, because the checking against zero will be quicker at the processor level, at the assembly language level. That's a good tip to know, that when they implement pipelining in the processor, they took advantage of the fact that most programmers will probably lean towards doing it that way to optimize that implementation. So, might as well take advantage of it and squeak a few more clock cycles out of our program. So little things like that the chapter points out, take that with a grain of salt. They're just good performance techniques in general when it's an option. I always kind of feel like, first of all, is get the logic right before you start optimizing. See the correct result once on the screen before you start spending too much effort optimizing your code to make it faster. After a while, after you've been doing it 10, 15 years, you'll write the optimized version of it to start with. But the first thing is just learn the language, learn the algorithms, and get the correct result. You got a lot of steps between what I would call now and going through the entry-level software developer stage and ... down the road towards, okay, now I'm an experienced programmer that can write optimized code. A lot of the algorithms that you'll probably want to learn how to implement in that middle gap in there can be much more challenging to grasp and implement, like searching a tree data structure breadth first. If you're trying to implement that algorithm, implement the algorithm first before you start trying to worry about the little nitpicky trying to eke out a few more clock cycles, right? And if you're trying to worry about the optimizing part of it first before you figure out how to implement the algorithm first, it can be really challenging. So just do things kind of in order. That's my recommendation. Last time I talked about that we were going to go over desk checking and tracing and unit testing, those kind of concepts, and then I just sort of skipped it at the end and didn't go into it. So if I can get through the chapter on looping quickly, maybe we'll go over some of that at the end, and I won't shortchange you again. But nobody brought up the fact that, hey, Dr. Schneider, you said you were going to go over desk checking either. So, some of that I can put on you guys too. I did notice the comment too about the the fact that some of these modules have the lecture video, some of them have the PowerPoint. I mean, there's nothing nefarious going on there. I'm not trying to be tricky about it. Some of these lectures, before we got the technology to be able to record the lectures, all I had was the PowerPoint, so I made that available. Some of them, I didn't have the lecture immediately, so I gave you the PowerPoint and the lecture. Some of them just have the lecture. My feeling on my PowerPoints is it's sort of like my notes. It's just sort of the outline of what I want to talk about. I don't know that that provides you guys any value, especially if I take the liberty of putting a bunch of animations in them. Animations don't translate well to you just opening up a PowerPoint file and looking through the slides. It's not a very high fidelity means of translating or transferring the information to you. So I just, it's like when we do pseudocode for an algorithm. Sharing the pseudocode with somebody, and when you've got the program done, just give them the program, right? But if all you have is the pseudocode, yeah, sure, the pseudocode will convey the information. So anyway, that's just a couple of minutes on what you're seeing in Canvas. Don't worry too much about it. Just take advantage. Just know that if I have it available, I'm giving you the best material that I have available there. So there you go. Okay, very similar to last unit on selection. Putting this one back up here, but now I've got repetition highlighted. So this is the third of our 3 control structures when we talk about structured programming. So we have a block of code, and we're going to be able to execute it repeatedly. Yeah. As before, there's a bunch of different ways that we can do this, different patterns that you'll put in your toolbox and pull the right one out when you need it. And we'll just kind of go over those. I threw together this little diagram just to illustrate just a way in your head that you can visualize these 3 control structures. The sequence one is simply the fact that your instructions are going to execute in order from top to bottom. No surprise there. Selection means that we get to a fork in the road and we can say, if this condition is true, do this, else that. And then repetition kind of looks like this more hairy looking one on the right, where, and I guess what I'm trying to convey here is with repetition, we have not added any new magical features to the language. All we're really doing is saying, if this condition is true, go outside the loop and go execute what comes next. If it's still false, then execute this set of instructions again, with the addition of, at the end of this block of instructions, go to the top of the loop and do it again. That's all we've added. If you look at the similarities between these two, the middle one, if I put a go to the top, then it's going to continue branching back up to the top. And then if I say, okay, if I'm done looping, then exit out, they're exactly the same. We're using the same building blocks as we did with selection. I don't know if that's helpful at all to see that visualization, but there it is. Okay, so this is, again, probably repetitive from COP 1000, but no matter what pattern we're talking about, whether it's a for loop or a do while, no matter which one we're talking about, they all still have these components, any loop. And, I try to drone this out there so that one of these days, when you're sitting at your desk trying to figure out why your loop isn't working, you'll hear my voice in the back of your head saying, did I set my initial condition? Did I check it? Did I modify the loop condition inside the loop? Oh yeah, I forgot that. I forgot to do that. That's why I've got an infinite loop. So you always want to check these pieces anytime that you're making a loop. And the big difference there is between some of the patterns is where we check the condition. So sometimes we check the condition at the start of the loop, that's the while keyword. Sometimes we do it during the loop. That's where we basically make an infinite loop and we have a break statement somewhere inside the loop. And then sometimes we do it at the end of the loop, which is the do ... while pattern. Okay, so Java supports all of those. Okay, so we get into the examples. Here's the first example, and I just pose a simple problem just to use as a basis for illustrating these. So let's say that we're going to use a random number generator and we're going to get a random number between 0 and 1 inclusive, right? So when I say next int, I'm either going to get a 0 or a 1. And then I'm going to loop while it's heads, basically, or I get the value 1 back. So this is what that loop would look like. While, you always have to put your condition in parentheses in Java, and then the work that needs to be done always goes in close braces. You remember in Python it was all indentation based, but in Java it's curly braces. So this print is representing the work that needs to be done. You know, in any meaningful algorithm, you're probably going to have more than just a print statement in there. Probably going to have some calculations, some, you know, whatever. And then at the end of the loop, in this case, I'm modifying the loop condition. You know, value equal to 1 is my loop condition, and I'm modifying that potentially by getting the next random number and assigning it to value, which would cause this condition to need to be reevaluated to see if it's true or false. So that's the simplest loop example that I could come up with in Java, and it illustrates our first pattern. So in this one, where am I checking the loop condition? At the beginning, the middle, or the end? It's not a trick question. Where? Somebody guess? At the beginning, right? So my loop being this while block, so I'm checking the condition at the beginning. I'm modifying it at the end, but I'm checking at the beginning. So of our 3 patterns, checking it at the beginning, the middle, or the end, this one is the example where I check the loop condition at the beginning. So if I come in here and the very first random number is a 0 for tails, what's going to happen when I get to the while statement and evaluate the loop condition the first time? It's going to be false, right? So it's one good thing to note about this pattern is I might never do the work inside the loop with this pattern. The very first time it could be false and I never execute what's inside. So we would say that the body of this loop executes 0 or more times. And also, another thing that you'll notice about this kind of a pattern is it always seems kind of wasteful to me to have basically the same line of code twice. And I guess as a programmer, I've always thought I should be able to write my program in a way that I don't have any repetition of code. Why do I have to have the same line of code twice? Isn't there a pattern that I can use where I can eliminate that? In this case, it's common to this pattern that we have what we call a priming read. So if you hear me use the term, or the book uses the term priming read, the only thing they're talking about is the fact that I have to call this line of code once before I start the loop. And then, yeah, you're going to have it duplicated at the end of the loop because I got to modify the loop condition. So we're kind of priming the pump is what they're talking about here by setting value to the initial value, and then we go into the loop. Okay, so this pattern requires a priming read. Why do they call it a read? Well, because often you're reading data from a database. So you'll say read first record, and then inside the loop you'll say read next record. Okay, next example. Simple example number 2. the priming read is gone, right? I only have that line of code once here inside the loop. I've set it to an initial value just so it's not uninitialized. That's fine. But I didn't have to do a priming read. And so we would say that this one is reading or checking the loop condition at the end of the loop. Another syntax thing, you notice here on the first example, I don't have any semicolon, but I do on the second example. I have a semicolon out here at the end. That's just a quirk of Java syntax for the compiler to parse your Java. Similar in C++, you have to do the same thing syntactically. If you're going to put the while after the curly brace, it needs the semicolon there to terminate the statement. So anytime you start a loop with do, then after the curly brace, it's going to look for and expect a while and a semicolon at the end of your loop condition. You know, it reads fine. It makes sense if you just read it, but here you don't have a semicolon, and here you do have a semicolon. And the book points this out too, that this is a common source of an error. If you put a semicolon in this first example, if you say while value equals to 1 semicolon, then you've said loop forever while value is equal to 1 doing nothing. And so you've immediately created an infinite loop. I don't know, the latest Java compiler, it may give you a warning and say, did you mean to do that or not? But it's technically an error if you put a semicolon after the loop condition in this pattern. So just get in the habit of knowing that this is the correct way to do it. And this is the correct way to do this pattern. Okay? But essentially we're doing the same thing. You know, we print heads as long as I've got heads. We get the next random number. Then at the end of the loop, we check the value to see if it was heads, or if the next value is heads. And if so, we continue looping. We go back to the top. As soon as the loop condition's not met, then we fall out the bottom of the loop and we do something different. But if we go back and think about our edge case, what happens the very first time through the loop? I can't stop it, can I? It's always going to do the work inside the loop regardless, because I don't check to see if I'm done looping until the end of the loop. So that, just realize that's one aspect, one property of this pattern is I will always do whatever the work here is that we encode into our algorithm once. Then I check the loop condition. And I would say the first pattern is more common, but you know, every now and then it looks better or fits the situation better to use this pattern. And whether you decide to use it commonly or uncommonly, you will see it, so you need to know how to read it when you see it in other people's code. Okay, third one. So same problem. We're going to get random numbers and we're going to check to see if it's heads or tails and print it. However, this is that other pattern where we check for the loop condition in the middle of the loop. So we've got the pre-test, the post-test, and I call this one the mid-test. You'll see different books, different authors call it something different, or sometimes they don't talk about it at all. But, you know, to me it makes sense. You got the check at the beginning of the loop, check in the middle of the loop, check at the end of the loop. But you see what they're doing here. We get the heads or tails value, and if it's 1, we break manually out of the loop. This is technically, I guess, described as being less of a structured design pattern than the other ones. But again, whether you decide to use it or go on a religious battle to eliminate it from our universe, you will see it in other people's code. So just know that that's what they're doing. It's just a plain old loop. They're just doing a mid-test check of the loop condition. So would you say output-wise or functionality-wise, this is more similar to the first pattern or the second pattern in terms of our edge case? Or what happens the first time through the loop? Yeah, closer to the first pattern, isn't it? Because I can break out of this one the first time if I don't get heads, just like the first one. The work doesn't necessarily get executed every single time like the second pattern. And I don't require my priming read on this one. That's another attractive thing about it. And I should say, you know, sometimes, again, the priming read here is simply get the next integer from the random number generator. Very easy to do. Sometimes setting up the initial loop condition, maybe it's 4, 5, 10, 20 lines of code to initialize that situation. And then all those lines have to be copied at the end of the loop to get the next item. And if it's a substantial amount of work, you want to try to avoid copying and pasting all those lines of code as your priming read and then at the bottom of the loop to continue looping, right? Here it's kind of like, well, why would I ever care about the priming read? But in some cases you do care about saving, not having to do that priming read. So this has the attributes of the first pattern in that I can short circuit it and get out of the loop the very first iteration if I need to, and I didn't have to code a priming read. But, you know, I have this ugly looking if statement that some people consider non-structured in the middle of my pretty loop. So I would say another advantage of this, notice my value here is declared inside the loop, inside the closure of this curly brace, you know, so the scope of that value variable is inside this curly brace scope. You know, there's a general philosophy in programming that when you declare variables or allocate memory, you want to tighten it to the smallest context possible so that you don't lose track of it. Like in general, global variables that are accessible from the beginning of the program execution to the end and accessible to and by everybody are generally frowned upon, right? You want to not do that. This is more ideal because you have simply a variable that's as tight a scope as you can get it for the work of this block of code. If we go back and we look at the first one, see, I had to declare my value outside of this scope, and it's got function scope. I had to declare it at the function level, right? So it's a little bit broader declaration. So, you know, if we're splitting hairs, this example 3, the variable has a little bit tighter scope, so that's good too. So this does have some advantages, some commonalities and differences with the other patterns, and that's what we're here to talk about, so I don't feel bad about pointing it out, even though I'm belaboring the point a little bit. Any questions about any of this? Have I lost everybody, or is it making sense? Okay. All right, so now there's the until. When we're talking about COP 1000, you know, in general, talking about all the patterns available to us in various different languages in programming in general, you usually talk about the until keyword. You know, sometimes I can loop until the condition becomes true as opposed to while the condition is true, is how we would read that. But in Java, we don't have an until keyword, but that's all right. We can do it anyway. All we have to use is the not operator and a little Boolean logic. As you can see here, while value is equal to 1 is exactly the same as saying until not value is equal to 1. They mean the exact same thing, I guess, language, or in the English language, even though in Java we don't have this keyword until. And if we were to decompose this expression, we'd say value not equal to 1. So while value is equal to 1 is the same as until value not equal to 1. So all I have to do is flip the Boolean over. And just a reminder, as we pointed out when we were going over the conditional expressions unit a few weeks ago, when I do that for an equals or a greater than or less than symbol, you have to add or remove the equal sign when you do that. But it works exactly the same way. You just have to add or remove the equal sign when you decompose this expression. Make sense? Excellent. I'm disappointed I didn't hear any chuckles from the back row about my pun. But that's okay. I'll move on. Didn't I just do simple loop 3? Okay, I have an off by 1 error, I guess. Haha. Okay, this is a different kind of example. I switched problem on us. So let's say, frequently in programming we have algorithms where we want to count things. So my problem here is I want to print a list of integers. Okay, simple problem on purpose, but I just want to print the numbers 1 through whatever number the user gives me and wants me to stop at. So I'm going to start at 1. If they give me a 5, I'm going to print 1, 2, 3, 4, 5 on the screen. No big deal. But this pattern is so common that we get special ways of doing it. I don't need those special ways of doing it because I can use the tools I've already got, similar to with the until. I don't need an until keyword because I can do what I need to do and do the same thing in Java using the while and the not operator. So here I can do a counted loop with a while by simply setting my initial condition to where I want to start, which is 1 in this case. I keep looping while the number I'm on, index, is less than the number where I'm supposed to stop, my ending point. Here's the work. I'm going to print the number on the screen. That's the work that I need to do in the loop. And then my modifying the loop condition is simply to increment the variable by 1. So another simple pattern of a loop. It's just that instead of the Boolean true and false heads or tails example, we're just counting things. So I'm going to keep counting until I get to this number. There's a little bit of care to be taken with these loops with the off by 1 errors. If I leave off the equal sign, then I'm only going to get 1 through 4 if they pass me a 5, right? So you got to take care, and that's why we want to check our code and make sure that it's working correctly, to make sure that we didn't forget. Lots of times when we're desk checking our code, it isn't because we didn't know how it should be implemented. It's because our fingers did something different than our brain intended. I always thought it was interesting. I got to a certain point in my career where my fingers were nimble enough and I could type fast enough that I could send, it's like a printer. Printer has a buffer. You send it a file and it doesn't print it all as fast as it receives the data. It buffers it. And then let's say it has this 1 megabyte Word document in its buffer, and slowly it prints line by line by line, and maybe it takes it 30 seconds to print the document. Okay, well similarly, I think our brains have a buffer for our fingers, and so I can imagine here's the text that I need to type, but then once I've sent that to my fingers will keep typing for a while. I had this happen dozens of times where I'd be typing and somebody would come in my office and ask me a question, and I would be listening to their question and answering it, and then all of a sudden in the middle of a sentence my fingers would stop typing. It's like, oh, I guess they ran out of buffered text to type, and so they just stopped. But the other thing I noticed was whenever my attention went to the person to listen to what they were saying, my fingers started typing phonetically. So whereas my brain would send TWO to the fingers would print TOO. And I'd look at what I just typed and I'd have all kinds of spelling errors. It still printed what I meant to, or typed what I meant to type. It was just not spelled correctly often. So that part of the brain, I guess, needs a spell checker that handles the buffering. But anyway, neither here nor there. Yeah, but another thing is, we have these wireless keyboards, which is all great and all that. But one thing I notice working with wireless keyboards, often it drops keystrokes or it repeats keystrokes. So there's all kinds of excuses as a programmer that I can come up with where creating this logic error in my program wasn't my fault, okay? But regardless, that's the reason. All of those things outside of our control, in addition to every now and then we just did it wrong, is why we desk check our program. So look for these little off by one errors and things like that. And I'm telling you that because I know you'll eventually write an off by one logic error into your program, but you'll be confused as to why it happened. And I'm hoping that you'll remember this conversation and think, oh, yeah, I should look for that kind of error. And when you're testing your code or somebody else's code, you need to be aware of what kind of errors can happen so you intentionally look for them. So I used to ask this question on quizzes and tests and stuff. We would talk about the makeup of a modern software development team. This was back in the, I guess, mid to late 90s, early 2000s. Microsoft kind of had this pattern for a software development team, which was you have a program manager that communicates the needs of the customer. You have the programmer who's writing the code, and you have a tester that is responsible for making sure that what the programmer wrote meets what the customer asked for. So it's this three-legged stool, as it was described, and having all three legs of the stool make sure that your team can stand up appropriately. Right? If you take out any one of them, then you start having problems. And Microsoft at one time had a 1-to-1 ratio between programmers and testers. And it wasn't always like that in every team. Maybe this one team has twice as many developers and only a few testers. Some other teams are very important. They have many testers and not as many developers, but overall, over the whole company, it was generally about 1-to-1. So being a programmer that doesn't write code, you could get a job as a software tester, and it's really interesting because you are tasked with creatively trying to destroy somebody else's work. It's like, okay, and the mentality that you want as a software tester is, I'm just going to assume that you put bugs in your code and I'm going to go find them. You might be the best programmer on the team, but darn it, I'm going to find the bugs. And the mentality part of it is important, because if you sit down and you say, oh, that person, Jeff is a really good software developer, I'm probably not going to find anything. Well, guess what? You're probably not going to find anything. But if you assume that that developer has bugs in their code and you just need to keep testing until you find them, well, you probably will find them, because everybody has lines of code. On the other hand, or has bugs in their code. On the other hand, when I started learning about these concepts, I started thinking, well, I think I'm a pretty good software developer. I wonder how many bugs I have in my own code. So I started doing this to, I'd write 20, 30 lines of code, and then I'd go back and I'd test my code, and I kept a little post-it there, and I would write down every time I found a bug in my code. Sometimes it was a typo, sometimes I left off an equal sign, it was an off by one error, whatever it was. I would just write down a little, and it was just me, so I was pretty honest about whenever I wrote down the little things. And come to find out, I averaged about one bug per line of code. over time. Maybe I wrote 100 lines of code in a day. I probably typed and fixed about 100 bugs that day as I was writing the code. So you can still be a good programmer and still create lots of bugs, and you need to understand both sides of it. What makes a good programmer, what makes a good tester, and be able to put on both hats to be effective and write quality code. The worst thing that you want is to write the code, the spaceship launches, sends the orbiter to Mars, it circles the planet for a while, and then it's time to change the orbit, and it smacks into the planet. Houston, we've lost communication. Can you tell me what the telemetry looks like? It's like, yeah, it crashed into the planet. What did you do wrong? And there was some French lander that did that, and they came down to looking at the code and assessing what happened, and turns out somebody hadn't converted inches to feet or some unit conversion properly, and so instead of going around the planet, it smacked into the planet. So stuff like that does happen, and that's not when you want to find it. You want to find it before you hit the save button, not when the lander smacks into the planet. Okay, anyway, point made. But anyway, what I would ask on these tests was, who on the software development team has the role of trying to make sure that the software doesn't ship? And, it's a little tongue-in-cheek, but if you think about it, the answer is that the software tester wants to make sure that this code never ships. You want to have the attitude that the code is never ready to ship because there's always one more bug out there. And the idea is the manager is sitting there watching the performance of the team day by day by day. And if the rate of bugs that the testers are finding starts to tail off to a certain point, and they're finding fewer and fewer and fewer bugs per day, you're never going to find every bug. But when the rate of detecting bugs gets to a certain level, you figure, okay, we're probably ready to ship. And then you'd make the decision to ship anyway, right? So that's the answer to the question. Whose motivation is to not let the software ship? The tester. Because the tester assumes that there's always one more bug out there that needs to be found, representing the customer. Okay, so I say back in the mid-90s because nowadays there's this idea, even at Microsoft, the political landscape shifted and a certain vice president got promoted through the ranks. I won't mention their name, but decided to let go many of the QA teams across Microsoft and thought, you know what? I bet the stock price would go up by $1 if I fired all the testers and made all the software developers test their own code. Which anybody who knows anything about software testing knows the worst person that you can have test a piece of code is the person who wrote it. Because of course in your mind your code works, or you wouldn't have checked it in, right? Of course you think it works, so you're probably the worst person to have the frame of mind, the state of mind to try to find bugs in your own code. I can attest to that 100 times over, seeing the code that people turn in. When people turn in their assignment and it's obvious to me that this code doesn't even compile, let alone run, I'm sure you never saw it produce the correct results because it doesn't even compile. Okay? And many developers have similar attitudes. Oh, I just changed something simple. I don't have to compile it again. I don't have to retest it again because I just changed something simple. And then pretty soon all the bells and whistles start going off and the landers start crashing into the planet instead of orbiting. So anyway, enough about that rant. Back to, I don't know how I got off on that, but back to counting. Okay, so this is a simple while loop that counts from 1 to some number. And I could have just put end equals 5 and made it a little bit simpler. But one of the difficult hurdles that people in programming find is that you're doing okay with sequence, and then selection. Yeah, okay, that's a little tricky, but I can figure out how to produce algorithms with if statements. Yeah, okay, I get that. And then for some reason loops, and they're just like, okay, I'm just lost. That just goes clear over my head. And you have to start thinking abstractly, right? The starting point can be variable. It doesn't always have to be 0. It doesn't always have to be 1. It can be some number that the user entered, right? And the difference, if you can get past this point in your mind of realizing that index is a variable, and while the program is running, it's going to occupy a different state, right? It's going to have a different value in it the first time through the loop as opposed to the second time through the loop, etc. Then if you can get your brain to grok that one little concept or technique, then it's like a eureka moment, and lots of things start become easier for you to solve. And same thing here. Here I made the ending point of the loop, the ending condition, be a variable instead of a hard-coded number, just to sort of reinforce that fact. So I'm going to start at 1, a hard-coded starting point, but I'm going to keep looping until my variable reaches this abstract value that got passed into this function. But that's all we're doing here. Other than that, it's just a plain old while loop. Okay, and I point this out to point out the next example, which is much simpler. So because counting in programming is so common that they give us a shortcut way of doing it, which is the for loop. That's the for keyword that we're learning about in Java. In Python, they like to use the range object. You create a range object, which is a set of values from one starting point to another starting or ending point. We don't really use ranges in Java. We just say, I want the variable to start at this value. I want to keep looping until the variable gets to this value. And here's how I want to modify the loop variable. I hope that it's obvious from the way this is constructed that I don't have to count up. My loops don't always have to start at a value and add 1 every time. I could make this index minus minus, and I could start at a high value and subtract 1 each time through the loop until I get down to a low value. I also don't have to just count by 1s. I can count by 2s or 4s or whatever value I want to. This index plus plus, what you put in here between this second semicolon and the parenthesis, is a Java statement. You could call a function there that determines how much to increment the variable by. Whatever you want to do. But again, you have to kind of think of it abstractly. And if you think, oh, this for statement has all the same lines of code as the previous example did. There's my index equals 1, there's my loop condition, there's my modifying it. That's all we're doing. We're taking those pieces out of this pattern and just putting them in here. There's a syntax where you can do multiple things here too. I could say index 1 equals 1, index 2 equals 12, right? It's just Java code. I can put more than one thing in here, in this part of it, in the initialization. And the only thing to remember is this is setting my initial loop conditions, so this part of it is only going to run the first time through the loop. This is like my priming read. This is my initialization. This one is going to get queried, evaluated every single time through the loop. When I get ready to go through the loop again, it's going to evaluate this condition. And then at the end, before it repeats, it's always going to call the code that I put here. That's all it is. It's just shorthand for the previous one. But boy, it looks cool, doesn't it? So if you're going to count stuff, this is definitely the preferred way to write the code, using a for loop. Okay. There's other patterns. I'm not going to belabor them because you probably should have had those in COP 1000, and there's nothing new that Java introduces. But nested loops is simply putting loops inside loops. You can put if statements inside loops. You can put loops inside if statements. You know, you can put loops with if statements with loops inside. You know, you can mix and match all this stuff. To the rules of structured programming, it's just that every one of these little substructures has to have a single point of entry, single point of exit, like we talked about. Where you'll commonly see nested loops is sorting algorithms. Like if you Google a bubble sort in Java, it's a nested loop. For I equals 1 to number of rows, for j equals 1 to I minus 1 or whatever. But it's nested loops. If I'm dealing with tabular data, like if I say, hey, print in rows and columns the multiplication table. I think that's one assignment that I like giving in Python. But if you're going to deal with tabular output like that, you're going to have one loop for the rows and the inner loop is going to be for the columns generally. So you'll use it in that kind of thing. Any kind of two-dimensional data. I guess three-dimensional data, you could have a loop within a loop within a loop. Then you'd have three-dimensional data. Yeah. There's another thing that I wanted to talk about here when we start talking about loops, because often, well, I guess historically, one thing that loops are often used for is for report generation. If you're creating a report, you know, in the old days, we used to print stuff on paper. And so you'd print a page of data, you'd get to the end of the page, you'd issue a page break, and you'd start at the next page. And you always had to count how many lines you'd already printed, so that you knew when you got to the end of a page, and then you could skip to the next page. Well, there's this thing called a control break, and like I say there, this is not to be confused with what we were talking about earlier with the mid-loop test using the break keyword in Java. This is just what we call them. We call them control breaks. So for example, when you get to the end of the page, sometimes you have to stop and say, here's a line of subtotals for all of the records on this page. Well, that's a control break. You're counting how many lines I've printed. Oh, I got to 50 lines. So stop, do this extra code, and then continue looping. Okay? So that's called a control break, that kind of logic. Yeah, and it's just a normal loop, but it's an example of where you'd have an if statement inside a loop. The book also talks about, I usually don't belabor this point too much, but it does talk about definite versus indefinite loops, and this can be kind of confusing sometimes. The strict definition of definite loops that I use, trying not to confuse everybody, is when you start the loop, when you get on the statement of code where the while or the do is, do you know how many times the loop is going to execute at that point? If so, then it's a definite loop. The place where this gets confusing and where you might get tripped up on a quiz or a test or whatever is if I ask the user to enter how many times they want me to loop. Now, does that become definite or indefinite? Well, you might say, well, I don't know what number the user is going to enter, so maybe it's indefinite. But no, you ask the user to enter the number and they enter 12. Okay, now when I get to the while statement and it says while my counter is less than or equal to this variable and the variable contains 12, oh, well then I know it's going to loop 12 times. So that's a distinction I'm making. When you're entering the loop, if it's already determined or determinable how many times it's going to repeat, then it's a definite loop. It's a definite loop pattern. Okay? So what is an indefinite loop? Well, when I say while true, okay, well, that's an infinite loop, so it's indefinite. I don't know how many times. I don't know when the sun is going to explode and cause a computer to not exist anymore and the loop stop, right? Or I don't know when the user is going to hit the close button on the window, which causes Windows to end the process, which causes the loop to stop. right? So it's indefinite. But a more common place where you'll actually use it, because you probably won't intentionally create lots of infinite loops to have an example of indefinite, is you're monitoring a sensor, like a motion sensor, let's say. And you check the loop and it says, nope, no motion. Okay. Check it again, any motion? Nope. Check it again, any motion? You don't know how many times you're going to iterate with no motion before you get to a point where, has there been any motion? Oh yeah, there's been some motion. Okay, we'll start the camera. You don't know how many times it's going to loop until that condition occurs. So in that case, it's indefinite repetition. That's the distinction that they're trying to make here. And so that's the reason I pointed out, is it can be a little tricky if you're trying to reason it out. Okay, so that's it for the looping stuff. And as promised, I wanted to try to talk about a little bit about desk checking, if I could. So let me bring up IntelliJ. Yeah, let's say new project. Test loop, for lack of a better name.
We do need a JDK too.
Okay, let me see if my... Okay, yeah, so my hello world little example here is working. Can somebody remind me what it is to zoom in on my code? What the keystroke is? I thought it was Control Shift something.
Control Shift plus, I think. I don't know it's
Control
it's
Alt
this.
plus,
It is.
Alt Shift plus, there it is. Alt Shift plus.
I think you can change it.
Oh, you think it's like a menu item or something? Could be.
The key might work.
I just can't remember. Well, and every time you restart these computers, they go back to the configuration from before. So I would have to redo it every time I start class. So, all right. So I wanted to point this out because sometimes I notice that students aren't taking advantage of it. If you just hit the run button, like I did, to make sure that my program was working, I had my JDK, you just hit the run button up here, and it executes the code, hello and welcome, and here's our little counted do loop for 1 to 5, and it prints the stuff. Okay, easy cheesy, except that I would have said print ln. Yeah, now my output looks a little bit better, but it puts the hello on a different line from the other stuff. But especially with loops, like I said, when you get to this point where it becomes more abstract, it gets a little bit trickier. So I create a variable for upper limit. You know, sometimes you have a logic error. Let's create one. I'm going to delete the equal sign. So I want to print the numbers 1 through 5, but I run my program and I notice, what the heck is going on? I said 5 and it's only printing 1 through 4. Don't fail to take advantage of this little bug icon up here. And I hit the bug and it does a similar thing. It starts running. Got it. So now it changed to debug. I think if I click it again, it'll kill this one and restart it and start over at the beginning. So that was a breakpoint that it set. Okay, let me start this over again, see what it does. Okay, so in Java, in IntelliJ, I should say, the way this works is, if you don't have any breakpoints set, then it's going to just run the whole program full speed. But that's not what I want. I want it to stop. So I'm going to set a breakpoint on the very first line of code. So I do that by going over here to the space between the border and the line number, and I just click in there and I get the little red dot, and I can set as many of these as I want to, but for now I just want to set a breakpoint on the first instruction. Now when I hit the debug, it's going to run until it hits one of those. So there, it stopped on this line of code, and this little area down here, you can use it to evaluate expressions. Like if I say 5 plus 3, it'll say the result is 8. I can evaluate things if I'm curious what, what's some, and I mean, that's not very useful, but if I said variable name 1 times variable name 2 and hit enter, it would evaluate what's in the contents of those variables and evaluate that expression for me. Very useful stuff. You notice it already has this args inside the display here. That's because it's looking through all of the variables that are currently in scope when this line is executing. Well, this upper limit variable doesn't get declared until the next line of code executes, so it doesn't list it here yet. But args up here is a parameter, which is essentially a local variable in scope, and so it will show me the contents of this. It's empty, it doesn't have anything in it, so it's not very interesting right now. But I can see what the contents of each of these variables are at this point in the execution of my program, which is incredibly powerful. There are keystrokes, usually it's like F9, F10, F11. I don't remember what it is in IntelliJ, so I'm just going to hit the F10 button. No, that wasn't it. But there's a step over. Where is it? Oh, here it is, down here. F8. Okay. So I'm going to hit the step over button, F8. Come on. Now, do I not have my function key lock? There we go. So I had to hold I don't know if your keyboards are like that or not, but I had to hold the function key down on this little wireless keyboard to get the function key to work. But F8 goes to the next line of code. It executes the line that I'm on where the breakpoint was and then goes to the next line of code. So when I'm talking about desk checking, I'm thinking about, all right, my cursor is sitting here on this line of code, line 8. I imagine, Mark the human compiler says, what is going to be the result on this computer if I execute that line of code? So in my head, I say, well, I'm going to allocate memory for a new variable, and I'm going to initialize it to 5. Excellent. Then I hit the F8 key to see if that's what actually happened. That's the mentality that you want to have is, what do I expect to occur? Execute the line of code and see, yes, that's what actually happened. If you just blindly go through there and hit the F8 key, stepping through there without putting any thought into it, well then why not just blindly run it? Why step through it? But the value add is for you to understand what's going on with the logic of your program. So think about what you think the result is going to be from executing it, then execute it, and then you'll get the value out of the debugger that you want to get. So, a couple of things there. Being able to step through your code and being able to examine the contents of your variables as you execute your code, hugely powerful. Okay. So I'm on the beginning of this loop. What do I expect to have happen? Well, I think I'm going to probably allocate another variable and set it to 1. And then I'm going to check to see if it's less than upper limit, which is 5. And if it is, then I'm going to move to the next line of code. I'm not going to do this line of code yet because that only gets executed at the end, so I wouldn't expect my I variable to go from 1 to 2 yet. So that's what I expect to happen. Let's see if it does. So I hit F8, it goes to this line of code. Now I have a variable I that's set to 1 and upper limit set to 5. Now what I expect to happen, I expect it to print I equals 1 on the screen. There's probably an output tab here. Yeah, here we go. Yeah, I equals 1 got printed on the screen. Okay, now I'm back up here. All right, when I hit it, now this time the I++ is going to execute. So when I hit F8 again, I expect I to go from 1 to 2 and then check against upper limit and go to the next line of code. Sure enough, I went to 2, checked against upper limit. Now another third really cool and powerful thing that you can do here is, let's see, do I have to, I want to modify this. Set value. So I can actually change the value. I'm going to set it to 4. So I just changed the value of that variable while my algorithm is running. Is that kind of scary? Now let's see what's going to happen. What did I get on the console? Yeah, so it printed I equals 1 and then it jumped all the way to I equals 4. Now if this loop was going from I equals 1 to I equals 10,000, yeah, I don't need to test. This is another software testing principle is you don't need to test every single iteration of every line of code. You can usually skip stuff. You don't have to try every possible test case that you can imagine. You can group them into things that have similarities or along themes, and you can, we call those equivalence classes, and you can test representative cases out of each equivalence class. Okay, so I skipped all the way to the end of the loop, and now I get to 4, and it exited. It did not do I equals 5. So there's my logic error. So I can then say right click, where is it? IntelliJ may not have this. Okay, so in C++ land, I think C# land too, there's this notion called the current instruction pointer. And it's, you know, usually an arrow pointing at the current instruction. Here it's indicating it by the highlighted blue line. In other languages and other tools, you can change where that is. Like you can usually drag that instruction pointer up and tell it, this is the next line of code I want you to execute. It isn't universal, and as you can see, it doesn't look like IntelliJ and or Java support that, because you can get into some really weird situations. What if I set the next instruction to a line of code where a variable hasn't been created or initialized yet, right? So you can get in some scary stuff there that they may not want you to do here in Java, which is fine. But in other languages, you can do that. So we won't demonstrate that. So I can change variables, I can alter the execution of my program logic, but that's about it. Wait, F8, there we go. So when I'm sitting there on the closed curly brace and I hit F8 again, it runs ahead and says, okay, I'm done. And that's kind of what I was wanting to show you, is that you can step into these algorithms and figure out what's going on. You know, I see my logic error there. I can see that, well, why is it comparing to less than? And I realize, oh, that's the reason why it stopped at 4 is because I needed to have an equal sign to make that condition stay until the value gets to 5 instead of quitting when it gets to 4. And I can fix my program and rerun it. And now I fixed my bug. Now it goes to 5 like I did before, and we're good. Okay? So that's desk checking, being Mark the human compiler, and imagining what your code is going to do before you hit the execute button. Stepping through your line of code, one line at a time, and being able to examine and evaluate expressions and change the value of variables as you're doing it. It's incredibly powerful. It's hard to impress that upon you when the kind of programs we're doing in class are just not that complicated yet. But as the programs get more complicated, and you've got a project that has dozens of Java files and thousands of lines of code, it will become much more valuable for you to be able to set breakpoints and run to those breakpoints and then step through your code when you hit those breakpoints. So, wanted to point that out, and that's pretty much it. Any questions? Okay.